This is the high-level topic of wave phenomena. It is an extension of waves. Describe the nature of standing waves, or stationary waves as they're sometimes called. The IB say that you should consider the energy transfer, the amplitude, and the phase. Now, a standing wave, or a stationary wave, is basically where the energy is trapped between two boundaries. The energy is not able to be transferred outside of the confines of these boundaries, compared to a progressive wave where the energy, or the wave, is free to travel away and therefore transfer energy away from the source. As far as the amplitude is concerned, in a progressive wave, the amplitude stays fairly constant over a short distance, but with a stationary wave, there's some areas where the amplitude is zero, which are called nodes, and some areas where the amplitude is at a maximum, and these are called antinodes. With a progressive wave, however, the amplitude does decrease because the energy spreads out. With a standing wave, the energy is trapped. I've already mentioned that the amplitude of the oscillation varies along the standing wave with its nodes and antinodes. And that the nodes and the antinodes show where there is a constant phase difference. For example, where there's an antinode, where there's a large amplitude, this is where one crest from one wave meets the crest from another, or a trough meets a trough. So you get constant constructive interference. A node is where you get constant destructive interference. In other words, the crest from one wave meets with the trough of the other, or in other words, the reflection, or the trough from the wave meets the crest from its reflection. One-dimensional standing waves. We'll go to this website and look at this. Okay, this is a driver demonstration which shows how a standing wave is formed. I apologize for the horrendous color scheme, but the demonstration is really quite impressive. It's a bit ugly, but it shows and it demonstrates very well this idea of a standing wave formation. Now what happens is you get a wave which is going from left to right. The original wave is red, and then it reflects at this point here. The reflection will be in blue, so you will be able to determine you will be able to see the two different parts of the wave: the incident wave, which is red, and the reflection, which is blue. What happens is that the two waves interfere, and you'll see now what is happening. Here is the blue reflection. Of course, when you see the standing wave, you don't see the red and the blue waves separately. You see the sum of the waves. The sum of the waves is demonstrated by the black wave there. It's the sum of the displacements. Now you notice here, for example, at this point here, you've got a double trough. That's why you get a maximum. And here again, a double crest. So there are some points where you notice here, which is the antinode, it oscillates between a double crest to a double trough. In other words, the amplitude is at a maximum value. At N, which is where the node is, notice that the crest and the trough interfere destructively. The incident wave and the reflective wave interfere destructively. So therefore you will always get a node there. So you get an alternation between nodes, and antinodes. So what we notice is that the wave reflects from the boundary, and there's interference as the wave interferes with its own reflection. We get areas of constructive interference, which are the antinodes, where the phase difference is 0 or m lambda. We get points of destructive interference, which are the nodes, where the phase difference is lambda over 2, or 3 lambda over 2, or 5 lambda over 2. In other words, 2m plus 1 lambda over 2, an odd number of lambda divided by 2. Remember that the wave changes phase on reflection at that fixed point, so it becomes inverted. Discuss the modes of vibrations of strings and air in open and closed pipes. Here we have a string which is secured at both ends. This is one possible standing. It's called the fundamental, or the first harmonic. If you increase the frequency, in other words, you double the frequency, you halve the wavelength. This is the next harmonic, the second harmonic, or the first overtone. This is 3 times the frequency. This is the next harmonic, and is the second overtone. As far as longitudinal waves, we can represent this by oscillating air inside an open tube. At the end of the tube, the air is able to oscillate. So this will be an antinode, and this will be an antinode. We have a node in the middle. This point here shows that in the middle, the amplitude is 0. The amplitude is a maximum at the end. This is the fundamental. This is the second harmonic. Notice that here we have an antinode. We have a node here and node here. The boundary condition is that at an opened, this will be an antinode. The third harmonic, here again, the boundary condition is that there will be an antinode here. So basically the boundary conditions decide which modes you have. Here we have another set of boundary conditions. We have open at one end and closed at one end. Well, if it's closed, it's not possible for the lateral movement of the particles because it's basically next to the wall. It has nowhere to go beyond the wall. So this will be a node. This is one of the boundary conditions. And the other boundary condition is that it's open at the other end. In other words, that would be an antinode. So on this particular closed tube, closed at one end and open at the other, this will be the fundamental. That will be the first overtone and the second overtone and so on. Now, a little trick about calculating the wavelength. This looks like, the wave looks a bit like 2 American footballs, like this. What you can basically do is divide it into quarter wavelengths to be able to find out how many waves you'll get there. So you need to count the quarter wavelengths. So this is 1 quarter, that's the next quarter, that's the next quarter. So we basically have 1, 2, 3, 4 quarter wavelengths. Which is 1 complete wave. What about the fundamental of the first harmonic? How many quarter wavelengths are there here? There's basically 1, 2 quarter wavelengths. So that's going to be half a wave. How many quarter wavelengths here? You basically have 1, 2, 3, 4 quarter wavelengths. In other words, 1 complete wavelength, and so on. How many quarter wavelengths here? We have 1, 2, 3 quarter wavelengths. So there you have it. Here we have a kind of problem that you might get. The waveform is 45 meters long. The open tube, or the tube which is open at one end and closed at the other end, is 45 centimeters long. What is the wavelength? You usually have to decide how many quarter wavelengths are there. 1, 2, 3, 4, 5 quarter wavelengths. So 5 wavelengths divided by 4 is equal to 45. So what is the wavelength going to be? So the wavelength will be 0.36 meters.